Okay, so the topic we're going to start now is vibrational modes. Of the ideal gas. In particular, we're going to look at, the diatomic gas. So this is a gas where there are two atoms in each molecule. And the critical point is we're going to take a very simple model of this. We're going to model it as a harmonic oscillator. Which is good enough to show us the basic behavior. So this means we imagine I've got one atom here, I've got another atom here, and we imagine that these atoms are connected by some kind of spring, a harmonic spring. We showed in this case, the energy levels epsilon n are just labeled by a single integer, and the energy is related to the natural frequency of vibration, h bar omega, times n plus a half, where n is a positive integer. Okay. Now these particles, I assume, are non-interacting. They're distinguishable. They're distinguishable because they are at high enough temperatures in different translational modes. So therefore, we get that Z, T, is, we use the formula we always use, it's the sum over energy levels, which in this case is N, of E to the minus epsilon N over kBT, all to the power of the number of particles. So we got a similar formula when we looked at the rotational modes. In the rotational modes, we had to do a density of states approximation at this point. So in the rotational modes, we couldn't do the sum. But it turns out that for this epsilon n, the sum is possible. So here we can calculate exactly without having to make a density of states approximation. Okay, so let me show you how it's done. We've done a calculation similar to this before already. Z of t is, so epsilon n is this. I can take the factor of a half outside. So this gives me e to the minus h bar omega over 2 kBt. That's taken the factor of a half. And I get the sum, n goes from 0 to infinity. And I've got e to the minus h bar omega over kBt to the power n. All of that. All I've done in this sum is the factor of a half comes out because it doesn't depend upon n. The sum upon n looks like something to the power of n. And then this is a geometrical sum, so we know the result. So the result for sums like this I wrote down last week, I think. Sum n goes from 0 to infinity of some number to the power n is equal to 1 over 1 minus that number, provided that the size of that number is less than 1. Which in this case it is, because it's a negative exponential. So in this case, A is just this Boltzmann factor. So this gives you the result that Z of t is e to the minus h bar omega 2 t divided by 1 minus e to the h bar minus h bar omega over kBt, all to the power n. And this is an exact calculation. We haven't made any approximations. Now what we're most interested in is the internal energy, how much energy do these vibrations hold, and secondly, the heat capacity of these vibrations. So what we want to do with this formula is find the internal energy stored in the vibrational part and the heat capacity, which I'll just call C. It has no volume dependence. Okay, and then this is again exactly the same as on the quiz. U of t is kBt squared d by dt, the log of the partition function. So I can bring down the factor of n d by dt of. So this first term, log of exponential, is just inverse functions, right? So the first term just gives me minus h bar omega over 2 kBt. And then this I've got log of 1 over something. Log of 1 over something is minus log of the same thing. So this is minus log 1 minus e minus h bar omega kBt. So I have to compute this derivative. So let's just do it, n kBt squared. So this is 1 over t, which gives you minus 1 over t squared. So this is h bar omega over 2 kBt squared. And you see that that will cancel nicely. This one I get plus, derivative of log is 1 over this. Multiplied by the derivative of this, which is h bar omega over kBt squared times e to the minus h bar omega over kBt. And this simplifies quite nicely. The first term gives me n over 2 h bar omega. The second term gives me n times h bar omega over e to the h bar omega over kt minus 1. Now the first term here, n over 2h bar omega, has a simple interpretation. What is it? You see this is a constant, right? It doesn't depend upon temperature. It's a constant shift in the energy. And where it comes from is here. The ground state energy of the particle is not 0, but the ground state energy is a half times h bar omega. That's the minimum energy the vibrational mode can have, according to this formula, is a half h bar omega. So if this is the minimum energy of one particle, then the minimum energy of n particles is given by this. So this is simply the ground state energy. At 0 temperature, the energy is not 0 because of this ground state energy term. But thermodynamically, it's not important because it's just a shift in the 0 point of the energy. It doesn't change the dynamics in any way. Okay, so the really interesting term is this one. So finally, we have to find the heat capacity. To do that, you need to differentiate the energy. So per particle this is. So we divide by the number of particles, then it's the derivative of u with respect to t. So this gives you h bar omega times the derivative of the second term over there, which is this, and the derivative of this, which is so that's the derivative, and if I simplify this, I can say that heat capacity is Kb times h bar omega over Kbt squared divided by e to the h bar omega over Kbt minus 1 squared. Okay, so what does this function look like? Well, first of all, if t is small, so in other words, if Kbt is much less than h bar omega, that means that this term, h bar omega over t, is very big. This is a big number, but on the bottom I've got the exponential of the big number, so this term wins. Therefore the heat capacity is exponentially suppressed. It goes like e to the minus 2, because of the squared here, h bar omega over Kbt. So it's suppressed exponentially. We can also look at the opposite limit. If Kbt is much greater than h bar omega, then this means h bar omega over kt is a small number. And in particular, this means we can approximate the exponential approximately equal to 1 plus. We can approximate the exponential like this. This is just a first order Taylor expansion, and this number is small. And if this is true, then CV takes a very simple form. This, you see that the top and bottom are exactly the same, so they cancel, and this just gives you that C, the heat capacity, is equal to the Boltzmann constant. And this is the prediction of the equipartition theorem. If I put these two things together, I can finally draw a graph. Heat capacity has a limiting value of the Boltzmann constant as a function of temperature. For small temperatures, it is exponentially suppressed, then it rises, and then at high temperatures, it tends to the limit of Kb. So this is the heat capacity this is the heat capacity of the vibrational modes of a diatomic gas. At low temperatures, there is virtually no energy stored in these modes, and at high temperatures, the energy increases proportional to T. So that completes the analysis of the vibrational modes of the ideal gas. I think this is a good time to take the break. So remember, for the diatomic ideal gas, there are three kinds of excitations. It can have kinetic, translational kinetic energy, it can rotate, and here, as we studied, it can vibrate as well. So after the break, we'll put all of these three forms together and give us our final equations for the ideal gas.